Okay, welcome to the sixth video in the Discrete Structures series, and we'll spend some time in this video looking at two specific concepts inside of functions that are really important, and these are inverse of a function, and then we have a composition of functions. So first about inverses. So let's say I have a function f of x, and this produces any output, let's say x squared, right? So what does it mean to ask the question what the inverse of a given function is? So it's essentially asking the question, what new function can I use to plug in all the outputs that I had from the first function to get back the corresponding inputs? So what would that function be? Even with some logical thought, we could say that the inverse of x squared would be the function square root of x, right? Because whatever number I square, if I take the root of it, I get back to the same number. So this function would be the inverse of this function. Now, why is this concept even useful? Because this has some implications on the concept of reversibility, right? So let's say this function is representing a process in real life. What does it mean for it to be invertible? The process can be inverted, right? The process can be undone, right? We can get back to the same state as we were before. So that has to do directly with the conservation of information. An existence of an inverse implies conservation of information. So why is that? If you think about it, if the inverse of a given function does not exist, it simply means that there is no way to get back to the inputs for at least some outputs, right? So in that sense, we don't have the information that got us to that outputs in the first place anymore. So invertible functions are those functions which completely maintain the information about the domain, right? So from the codomain or the range, you could completely calculate what the domain of the function was. So let us look at the idea of inverses in the context of Venn diagrams so that we could build some defining criteria about what is needed, right, for an inverse to exist. So consider this set A and set B, and there is some sort of mapping. I don't want to draw a mapping, but there is some sort of mapping between A and B. And I want to question about the nature of this mapping in order to make sure that I can revert back from B to A, right? So this mapping is from A to B. It's a function from A to B. And is that function really invertible? So we know the two defining characteristics of a function, that each element in the first set should be mapped to only one element in the second set. And that means that I cannot have configurations like this, where two elements have the same output. Even though this originally is a function, if I try to trace this element back, I don't know whether this output should be generated or this one, right? So there will be an ambiguity in the output. So that would mean that this inversion is not possible, right? And this kind of arrangement lost information because these two inputs are producing the same output, and by looking at the output, I cannot really tell which input I should go back to. So one criteria for the existence of an inverse is that the function must be injective or 1-to-1, right? Another criteria that we need to establish here, let's call this A and this B again. I also want to prevent situations like this. There's two elements in A, let's say, mapped to, let's say, two elements in B, and there is some element in B that is not mapped from any element in A. So even though this is originally a function, if I try to invert it, I cannot correspond this input to any output in A. And if I think this as a physical process, some set of inputs produced all of these outputs originally, but I don't really know which input produced this output, right? So I kind of lost information. You can always tell that the existence of an inverse implies conservation of information like we talked about earlier. But, these are the two defining characteristics, and this implies that the function needs to be onto. So injective or 1-to-1 and surjective or onto. So if these both criteria are true, this is a 1-to-1 correspondence or a bijective function, right? So this is one interesting criteria. A function has to be bijective in order for its inverse to exist. Only functions of this nature can really be inverted. So for each input, there is one and only output, nothing left in the output space. And if this happens, for each output, I can uniquely track back the input and no information is lost, right? So this is the idea of inverses. Let's look at this problem. So we're given a function fx equals ax plus b, and both a and b are real numbers. A, b belong to R, and it says a is not equal to 0. And it's asking me two questions. Is this function invertible? If so, what is the inverse? And it's funny, oftentimes in exams, this is kind of like a free question, right? Because this question would not be relevant if the answer was no, and you would see in exams that it's a 5-mark question and so on. So this has to be answered. Either way. So before we even dive into the problem, let's look into this particular thing, right? So assuming this function is invertible, for now, let's say a is not equal to 0. Why did the question really mention this, right? And this will come up later. This will be relevant. But immediately I could see by plugging in a as 0. What happens to this function when I plug in a as 0? When I plug a at 0, I get simply fx equals b, right? And for any x, I'm just getting a b, right? So it doesn't change by changing the input. From the output, there's no way to really go back to the function, right? So I put in 3, I get a b, whatever b is, let's say it's a 5. And if I change the input to, let's say, a 6, I still get a 5. So from the 5, it's ambiguous whether to go back to a 3 or a 6. Having said that, let's dive into the solution of this problem. The idea of bijection comes in here. We need to prove that there is a one-to-one correspondence between x and ax plus b in order to prove that this function is invertible. So we prove bijection in 2 steps. First, we prove that this function is actually one-to-one or injective. And then we go on to prove that the function is also surjective or onto. Okay, so this one first. So the idea of injective functions is that there should not be any 2 inputs that produce the same output, right? So if that happens, this function won't be injective. So we prove this by contradiction. We assume that there are 2 distinct or different inputs that are producing the same output, and we'll see that that cannot happen, right? For any reason, we want to reach a contradiction. So let's say there are 2 distinct inputs to this function, x1 and x2. x1 would produce an output of a x1 plus b. x2 would produce an output of a x2 plus b. And my assumption is that these are different, okay? So what I want to prove is that under no circumstances could these 2 be equal. But let's see what happens if we try to equalize them anyway, right? So that's how we typically reach a contradiction. ax1 plus b, let's say, is equal to, hypothetically, ax2 plus b. Then what would end up happening is this b would get cancelled. It would leave me with ax1 equals ax2. And remember that a is not equal to 0, right? Otherwise, I would not be able to cancel the a because I would just be cancelling 0 from both sides. That's not allowed. But since that's not happening, I can cancel and I would assert that x1 equals to x2. So here is my contradiction, right? So I started believing that x1 and x2 were indeed different, but what ended up happening by assuming this is that these turned out to be equal. This proves that the function is injective by contradiction. Going on to the proof for surjective or onto. So what does onto really mean? Onto means there's nothing in the output space that doesn't have a corresponding input, right? So the output space is completely filled. So how do we even go about proving that for a function like this? In order to see if for every output we can track its corresponding input, we want to undo the process that happened, right? We want to undo the process that took us from the input to the output in the first place. So let's observe what happened in this function. So I have x, I multiply it by a, and then I add a b. See, this is my first operation, multiplication. This is what I did first. And addition is what I did second, right? And when I'm undoing, I want to undo the second thing first, and then I want to undo the first thing last, right? So the undoing needs to happen in the reverse order. So let me try to write a new function that undoes this process. So first I take a x and I undo the process of adding b. So I subtract a b, and then I undo the process of multiplying with a, and that is dividing by a, right? So when I do this, I get another function. Hopefully all I need to prove now is that this function is still a real number, right? And that means that this particular input would have caused that output, right? And this would not leave any output without a corresponding input. And since this a is something that I cannot assume to be 0, this is bound to be a real number, right? So there I have my proof. But there's an easier way to do this. You would not obviously do this in your exams. You'd simply assume fx to be y, do something like y equals ax plus b, and solve for x. Whenever you solve for x, you are effectively undoing the process. So x in this case would be y minus b divided by a. And therefore, your inverse would just exchange the rules for x and y, right? So your inverse would be y or fx equals x minus b by a, right? So this function would be the inverse, like this one. You can further verify this by plugging this thing into the input of the original function. So what happens if I take f of y minus b divided by a? So let me do some algebra here. This should hopefully be equal to y. So that tells me that if I want to go back from y to my input, this is my input. So there is no y that doesn't have an input. So this function is surjective. So here we prove that the function is injective as well as surjective, right? So it means that it is a one-to-one correspondence and therefore its inverse exists. So since the function is one-to-one and onto both, and this is also called bijective, the inverse exists. Okay, so there could be another class of problems which asks you to prove that one function is the inverse of another. Not finding the inverse, but proving that two functions are inverses to each other. So let's say, prove that x cubed is inverse to x to the power 1 by 3. My claim here is that if a function fx is defined as x cubed, its inverse is x to the power 1 by 3. So f inverse x equals x to the power 1 by 3. So how do I verify if this is true? All I need to do is to plug this output as an input to this function, right? So let's see what happens. When I do f inverse of x cubed, which is the output of the first function, I get x cubed to the power of 1 by 3, and that is x, right? And how did I reach x cubed? I reached it via x, right? So I started with x, reached from x cubed, and then plugging x cubed in the inverse got me back to x. So these two functions are indeed inverses to each other. So if plugging in this would result to something other than x, these functions would not be inverses to each other. So that is a pretty easy way to prove the inverse property when two functions are given. Okay, so there's a very brief topic that I want to quickly touch about before concluding this video, and that is the composition of functions. So it's clear by what it states, right? We're simply trying to compose two or more different functions. So we do this all the time. Look at this algebraic expression. So let's say when I say, fx is equals to 2x plus 3, a random function. What I'm doing here is I'm composing two different functions, right? So first function is multiplying x by 2. This is my multiplication function. And the second function is adding 3 to the result. This is my addition function. So what I'm doing is I'm taking x, and there's a specific order of operations. I'm first plugging x to multiplication with 2, and then I'm plugging the result back to another function that adds 3. So this process of plugging the output of one function into the input of other functions and chaining them together is known as composition of functions. So in Venn diagram, let's say a very easy example. Let's say this is a function that maps 1, 2 to 2 and 4 multiplied by 2. And this is a function that adds 1. So it takes the inputs 2 and 4 and it produces 3 and 5. So how would I compose these functions? Composing this would result to one single function that takes a 1 and produces 3, takes a 2 and produces 5. A single function that is a composition of these two functions. So let's also see an algebraic example. Let's say fx is x plus 1 and another function gx is equal to the square of x minus twice its value, right? So x squared minus 2x. So I need to calculate f of g, right? I didn't mention this yet, but the composition of two functions is in general mentioned with this symbol. So this function would simply be the result of plugging the output of fx into gx, right? So this would be g of fx by definition, and that would be equal to g of x plus 1, and it tells me to square whatever is inside, x plus 1 squared minus 2 times x plus 1. So I think it's easier to take common here than expanding. X plus 1 take common. Here I get x plus 1 remaining. Here I have minus 2. So that's x plus 1, x minus 1. That's x squared minus 1. All right. So this is how you can compute the composition of different functions. So I think that concludes the discussion for this video. In the next video, we'll be looking at graphs of functions and some functions useful to computer science. So I'll see you guys in the next one. Have a good day. Bye.